Well, it's an ancient debate. It goes all the way back to the ancient Greeks about the origin of life. Is it the result of a purely undirected process, a material process, or was a designing agent or intelligence involved in some way? And that's an ancient debate, and it's popped up all over again.
Richard Dawkins has talked about this debate. Which side is he on?
Well, he's on what we call the materialist side. He thinks the undirected processes have done it. He says that biology is actually the study of complicated things that give the appearance of having been designed for a purpose, where the key word is, for Dawkins, appearance. Things look designed, but they're not really designed. They don't owe their origin to an actual intelligent designer of any kind.
And Francisco Ayala, he also has said that, and he's past president of what?
American Association for the Advancement of Science. And he says that it was Darwin's greatest accomplishment to show that the directive organization of living things can be explained as the result of a natural process, natural selection, without any need to invoke a designer or a creator of any kind. Another place he says that Darwin gave us design, the appearance of design, without a designer.
Now, give me the other side.
Well, the alternative view is the theory of intelligent design, which says that living things give the appearance of design because they really are designed, and that you can tell when you examine the scientific evidence. The theory of intelligent design is a pretty simple idea at root. It's the idea that we can detect the activity of intelligent agency in the effects that they leave behind. If you go to Mount Rushmore, for example, you see the beautiful faces on the mountains there, and you realize that a sculptor played a role. Now, inside cells, we don't have little sculpted faces, but we have other indicators of intelligence, digital code, complex nanotechnology, little tiny miniature machines, things that we would in any other realm of experience attribute to intelligence. So our argument is that what we see in biology doesn't give just the appearance of design, it's actually giving us evidence of an actual designing intelligence.
Now, you yourself, you struggled with these questions. You were a geophysicist at that time, and then you met a fellow that we had on the program way back in 1985. His name was Dr. Charles Thaxton. Tell me about how he influenced you and how you went to Cambridge.
Well, I got interested in the debate about the origin of life in a kind of odd way. There was a conference that came to the city where I was working that was examining that topic. And I was shocked when I attended the conference to find there were leading figures in the field who were all essentially acknowledging that we had no evolutionary account of the origin of the first life. I had thought that the evolutionary biologists had this all sewn up, but it wasn't the case. And on that, one of the scientists on that panel was a man named Charles Thaxton, who was living in Dallas, where I was living at the time. He'd just written a book called The Mystery of Life's Origin, in which he'd provided a really comprehensive critique of what was called chemical evolutionary theory, the attempt to explain the origin of the first life from simple non-living chemicals. And he made the case, and the other scientists from various persuasions on the panel agreed that we didn't have an explanation for this, and it was a question that Darwin didn't address in 1859, and it really hadn't been solved in the ensuing years. So I got fascinated with that, and a year later, when I went off to graduate school to England, I began to study that question, the origin of the first life.
Hi. Now, we've got the Darwin's Tree of Life up here, and explain, you just said that Darwin didn't have an answer for this thing. Talk about this Tree of Life.
Well, the Tree of Life was his famous depiction of the history of life. The vertical axis shows the the passage of time, and the horizontal axis is all the new form that arises over time. So if you look at the branches at the end of the tree, they represent all the forms of life that are on the planet today. And the idea in Darwin's theory is that new forms of life arise by a gradual evolutionary process that converts simpler pre-existing forms into those complex forms we see today. The simplest form, where the whole process starts, is represented by the trunk at the base of the tree. And Darwin didn't address the origin of the trunk, where we got the first life at the very beginning. And oddly, though there have been attempts to explain that since his time, 150 years on, we don't have any undirected evolutionary theory of the origin of life that is satisfying the scientific community.
Yeah, down there at the bottom of the trunk,
it's a mystery.
You had a mystery,
yeah.
And they used to say there was a prebiotic soup, and now there is no prebiotic soup. You've discovered that. But the fact is, the idea going at that time was there was some kind of soup, and the cell wasn't that tough a deal to unscramble. What did Huxley say about the cell way back then?
Exactly. In the 19th century, when Darwin first proposed his theory, it was fairly quickly accepted by a lot of scientists. There was debate, but eventually a consensus arose that Darwin had refuted the design argument. He'd shown that there was no evidence of actual design in nature, only the appearance of design. And yet there was a question that he never resolved, which was, how do you get life going in the first place? But scientists who were of a Darwinian perspective or persuasion didn't worry too much about that, because they thought the cell was simple and it was inevitable that we would be able to explain it in the same kind of way, involving purely undirected processes. And Huxley put it in a colorful way. He said that the cell is a homogeneous glob of undifferentiated protoplasm. It's like Jell-O or something, some goo.
But it didn't stay that way long. In other words, as science marched on, you got tools to better investigate the cell, and Operon came up with a theory for some of the new discoveries at that time. Explain his theory.
Well, maybe the first thing to say is that each time science discovered that there was more complexity involved in life than they thought, that the cell was a lot more complicated than they realized, then their ideas, scientists' evolutionary ideas about the origin of life, had to keep pace with that. So scientists had to come up with an account of that. And the first one to do that was a man named Alexander Oparin, who developed what was called a chemical evolutionary theory, or sometimes called evolutionary abiogenesis, life from non-life.
Mm-hmm.
And he envisioned not a one or two step process, which is what Huxley and others were thinking about in Darwin's time. He envisioned a 7 or 8 step process where you started from very simple chemicals that combined and recombined as various energy sources were supplied, and then they eventually produced the proteins that we knew about. And then after that, there was a cell, an enclosure that was wrapped around those proteins, and voila, that would be the first life. What Oparin didn't initially know about was the structure and complexity of DNA. It was really the discoveries that were being made in the 1950s by Watson and Crick and other scientists working on proteins. Watson and Crick studied DNA, other scientists studied proteins, and the more we learned, the more implausible this simple step-by-step evolutionary process began to seem.
When they finally got down to DNA, what was the big mystery? What is that your book is all about?
Well, there's 2 mysteries, and Watson and Crick solved the first one, which was the structure of the DNA molecule itself, and I would say associated with that is what it does. On the screen you see the beautiful DNA double helix with the chemical subunits that make up the molecule highlighted on the right. And there you see that there are some special chemicals that have little letters on them. And they're called, in chemical parlance, bases or nucleotide bases. And in 1953, Watson and Crick discovered the structure of the DNA molecule, but 4 years later, Crick had an incredible insight. I think it was a breakthrough insight in the whole history of biology, and it was formulated as a hypothesis that was subsequently confirmed by later discoveries, and it was called the sequence hypothesis. And his idea, which turned out to be correct, is that those 4 chemicals called bases function exactly like alphabetic letters in a written text or digital characters, zeros and ones in a machine code or a section of software. It's the specific arrangement of those bases that allow them to perform a communication function in the cell. The arrangement of those characters literally conveys information that allows the cell to build all the important proteins and protein machines that it needs to stay alive.
What you've presented to the people about DNA here, they can see those letters going up the spine there, and they want to know, okay, what is this code? What does it do? Why is it so important?
The information encoded along the spine of the DNA molecule directs the construction of proteins and protein machines. And proteins are the toolbox of the cell. They do all the important jobs. Just as in the toolbox you've got a hammer, a saw, a plane, and each one of those tools can perform a function partially in virtue of the specific shape it has. The same thing is true of proteins, that they perform different jobs in the cell based on their 3-dimensional structure. But what the DNA does is it provides the instructions for a whole complicated assembly machinery for building those proteins. It's a little bit like what goes on at the Boeing plant up in Seattle where I live, where the engineers use a technology called CAD/CAM, Computer Assisted Design and Manufacturing, where they're actually they will choose design parameters. Those parameters will be digitized, literally codified in digital code. That information will then be transmitted down a wire, and it will tell some machinery where to, for example, put the rivets on an airplane wing or whatever the mechanical part is. In other words, in our manufacturing technology today, we use digital code to make mechanical parts. Turns out the exact same thing is happening inside the cell. The digital code is stored on the DNA, and the mechanical parts are the proteins. And each one of them does a job in virtue of its 3-dimensional shape, just like the tools in your toolbox. You can't hammer with a saw because it's got the wrong shape and composition. Same thing is true in the cell. The shapes of the proteins determine the jobs that they do. And there are lots of intricate shapes. We've got some on the screen to my right. But
how many different proteins are there?
Well, there's thousands of different proteins inside cells, and each one of them has a very specific task that it performs, which is what keeps the cell alive. But the shape is critical. It allows the protein to do its job. On the next slide here, we have a protein that is involved in an enzymatic reaction. It's actually breaking apart a 2-part sugar. At the top of the screen, you see a little sugar that looks like a barbell. And you see how it nestles into a perfect shaped groove for the 2 parts of that barbell. And that hand and glove fit allows the enzyme to catalyze a breaking apart reaction that wouldn't happen without it. So it's again and again what you have is what's called specificity or specificity of fit. It's like hand and glove, and it's that beautiful intricate 3-dimensional shape of the protein that allows it to fit just right to do the job that it's designed to do.
every one of us have what? Trillions of cells in our body. This is what we're talking about, is what is in our body that you have discovered, and why did it blow your mind when you figured this out?
Well, it's the fundamental question. How do you get life going in the first place? You can talk about how it changes and evolves after it started, but if you can't explain where it came from, you have a huge gap in understanding. And in the 19th century, in Darwin's time, when he developed his theory, it was thought that the cell was simple. A simple homogeneous globule of plasm was one of the things that one of the scientists said. But we now know that the cell has an immense complexity. It's an integrated complexity, and it's an information-based complexity. Inside the DNA molecule, we've discovered that there's a 4-character digital code. Bill Gates says it's like a software program, only much more complex than any we've ever created. And we now know that the information in the DNA is crucial for directing the construction of other complicated molecules called proteins, which do all the important functional jobs inside the cell. They're the toolbox of the cell. So you've got information directing the construction of machines and complicated molecules that do all kinds of important jobs. So let's, if you don't mind, I'll give just a little tiny science lesson that explains how the information in DNA constructs the proteins. I've got some snap lock beads here, and I stole these from my kids when they were really young, and they've been bitter and twisted ever since. But anyway, the idea here is that each one of these snap lock beads represents an amino acid. Proteins are made of subunits called amino acids. There are 20 different varieties, and depending on the arrangement of those 20 different kinds of amino acids, the protein will form a different shape. It forms chain-like molecules, and depending on the arrangement, it will either make a shape like this, or maybe if you rearrange them, you'll get a different constellation of forces between these amino acids, and it'll make a different shape, okay? Now, proteins depend for their function on having the correct shape. So if you get the arrangement of the amino acids correct, then you're going to get the correct three-dimensional shape, and you'll have a protein will form that can accomplish a job inside the cell. So how does all that happen? Well, part of the answer is the instructions on the DNA molecule are directing the cell's information production apparatus to produce those proteins, but there's more to the story because that production apparatus is itself incredibly complex. It's a wonderful set, kind of machinery. So we've got some animation to show the whole process, not like in civics where you know how a bill becomes a law. This is how a DNA sequence becomes a protein.
How many amino acids actually form a protein? What's the smallest protein and what's the largest?
Well, the average protein is on the order of 300 amino acids in length.
All linked together, exactly right.
Right. And you have very short hormones that you can make with 8 or 10, but typically you need about 300. But some proteins are even, have thousands.
Yeah.
So it depends. It really depends on the job the protein's doing as to how complicated the structure needs to be, and therefore how many precisely sequenced amino acids need to be put in place.
Yeah, and again, folks, this information has got to be arranged completely right, or the protein will not form. The shape won't be there, and it won't do its job. It's a dead deal. Okay.
And it's the information on DNA that gets it completely right.
Now we're going to show you a little bit of this complexity, and the big question that we're going to is, where did this information come from? If you're starting from zero, could this information have come about by chance? Natural selection. All right, so let's watch this animation, and I want you to see this. Watch.
With computer animation, we can enter the cell to view this remarkable system at work. After entering the heart of the cell, we see the tightly wound strands of DNA, storehouses for the instructions necessary to build every protein in an organism. In a process known as transcription, a molecular machine first unwinds a section of the DNA helix to expose the genetic instructions needed to assemble a specific protein molecule. Another machine then copies these instructions to form a molecule known as messenger RNA. When transcription is complete, the slender RNA strand carries the genetic information through the nuclear pore complex, the gatekeeper for traffic in and out of the cell nucleus. The messenger RNA strand is directed to a two-part molecular factory called a ribosome. After attaching itself securely, the process of translation begins. Inside the ribosome, a molecular assembly line builds a specifically sequenced chain of amino acids. These amino acids are transported from other parts of the cell and then linked into chains often hundreds of units long. Their sequential arrangement determines the type of protein manufactured. When the chain is finished, it is moved from the ribosome to a barrel-shaped machine that helps fold it into the precise shape critical to its function. After the chain is folded into a protein, it is then released and shepherded by another molecular machine to the exact location where it is needed.
All right, folks, that's just one cell. All those little parts are in just one cell, and information is king. Information is controlling all of those different parts. It's even more complex than what Stephen just showed you here. Stephen, where did this information come from?
Well, that's the $64,000 question, as they used to say. It's I call it the DNA enigma, and the DNA enigma is not what is the structure of DNA. Watson and Crick solve that mystery. It's not even what does the information do. We've just seen it in the animation. The question is, where did the information come from? And there's two basic answers. Either the information arose through purely undirected, unguided, purposeless material processes, or it's the product of some kind of designing intelligence, in what we call intelligent design. Those were the two options, and that's what I set out to investigate as I became fascinated with this question in the mid-1980s.